In this problem, we will explore the properties of a model three-dimensional lattice of spins, each with spin s equals 1/2. Part A, what is the magnetic moment of each spin? What are the allowed values of the projection of the magnetic moment m sub I onto some chosen axis, say z-axis? Okay, so we have a spin system. So since this is a spin system, we have J, the total angular momentum quantum number, equal to capital S, the spin quantum number, which is 1/2. And the magnitude of the magnetic moment vector is given by lambda factor G square root J plus 1 Bohr magneton. So we have no orbital angular momentum contribution. Capital L is equal to 0 and capital S is equal to 1/2 spin angular momentum quantum number. So this gives us a lambda factor G, which is equal to 1 plus J plus 1 plus S plus 1 minus LL plus 1 divided by 2J plus 1, which is equal to, so you can see here this part is 0. So we have 1/2 times 1/2 plus 1, 3/2. So we get 3/4 plus 3/4, 6/4 divided by 2 times 1/2 and then 3/2. So that gives us 2. Because we have this is equal to 1 plus 1 is equal to 2. Okay, so then the magnetic moment of each spin will have a magnitude m equals G lambda factor is 2 square root J plus 1, that is 1/2 times 3/2 Bohr magneton. This is square root 3/4, which will give us square root 3/2 outside the square root. So this will be square root 3 Bohr magneton. And therefore, the magnetic moment of each spin will be square root 3 Bohr magneton in magnitude. Okay. And now we can find the projection onto some axis, say J axis, using the total angular momentum magnetic quantum number m sub J, which has values between -J plus 1 all the way up to J minus 1 J, with J is equal to 1/2. The only two possible values are plus or minus 1/2. So the projection of the magnetic moment onto the z-axis, mz, will have a magnitude minus lambda factor m sub J Bohr magneton. So this will give us two possible values, because G is equal to 2, mj is equal to plus or minus 1/2. We have two possible answers, plus or minus a Bohr magneton, for the projection of the magnetic moment onto the z-axis. Okay, so part B, what are the possible values of the magnetic energy of each spin? So let's say that we have a magnetic field H that is applied along z direction. In that case, we have a magnetic moment inside the magnetic field. The energy of the magnetic moment in the magnetic field H is given by minus m dot H using SI units. So this will be minus mzh because H is along z-axis and the projection onto the z-axis is mz. So we have two possible answers for the magnetic energy of each spin, plus or minus a Bohr magneton multiplied with the field, externally applied field, H. Okay. Now, part C, assuming that the spins are non-interacting, calculate the magnetization of the lattice of spins when a magnetic field H is applied along the z-axis. Hint, use the result from statistical thermodynamics that the average magnetization of a spin is given by 1 over z sum over I mi e to the minus ei over kt, where mi is the magnetization of a spin along the field direction when it has energy ei, and z is equal to sum over I e to the minus I over kt is called the partition function. Okay, so the partition function z is basically the sum of all possible e to the minus ei over kbt values, and we have two possibilities for the energy. It's either plus mu bh or minus mu bh. So we have e to the minus mu bh over kt if it's plus mu bh, and it's e to the plus mu bh over kt if it's minus mu bh. So this gives us, as you can see, e to the x plus e to the minus x. This is 2 cosine hyperbolic mu bh over kt, Boltzmann constant times absolute temperature. And if we let, as we did in the Langevin theory, alpha equals mu bh over kt, Bohr magneton times magnetic field divided by thermal energy, this is equal to 2 cosine hyperbolic alpha. As you can see, mu bh has unit of energy, kt has unit of energy, so alpha is a dimensionless quantity. Then we can find the average magnetization for each spin by considering 1 over the partition function sum over I mi e to the ei over kt. Okay, let's say that our magnetic moment is mu b along the z-axis. In that case, the energy for magnetic field along z direction will be minus mu bh, and because we have a minus sign here, it's going to be e to the plus mu bh over kt. Now let's say the magnetic moment is minus mu b along the z direction, then the energy is plus mu bh and the magnetic energy, so we will have e to the minus mu bh over kt divided by the partition function, which is 2 cosine hyperbolic alpha. So if I take this into mu b parentheses, mu b Bohr magneton divided by cosine hyperbolic alpha, and now I have e to the alpha minus e to the minus alpha over 2. So what is e to the alpha minus e to the minus alpha over 2? that is sine hyperbolic alpha. So mu b times sine hyperbolic alpha divided by cosine hyperbolic alpha. All right. So this is basically mu b times tangent hyperbolic alpha. So we obtain average magnetization per spin to be equal to mu b times tangent hyperbolic alpha. So the total magnetization will be capital M. It will have contributions from all the spins. So we will have n times m. Basically, what we have calculated here is the average. It says the average magnetization of a spin, but we're basically calculating the average magnetic moment of a spin, right? So this is basically, unfortunately, not quite right. It's the average moment, magnetic moment of a spin. And then in order to go to magnetization, we have to multiply this with the number of spins per volume. So if we say n is the number of spins per volume, we will have the total magnetization equals n mu b tangent hyperbolic alpha. So we have to add up the contribution to the moment from each spin and find the total magnetic moment and divide it by the volume. That's magnetization. So that's what we have done here. Now, for a given value of field H, how does the magnetization M depend on temperature? Explain the behavior of magnetization for T approaching 0, taking the number of spins per unit volume to be 3.7 10 to 28 per meter cube. Calculate the numerical value of the saturation magnetization Ms at T equals 0. Explain the behavior of magnetization for T approaching infinity. Now we know that for a given typical external magnetic field in the lab, typical H value, we have this approximation alpha mu b h divided by kt is much less than 1. So it's a very small number, so that we can use the Taylor series expansion of tangent hyperbolic alpha as alpha gets closer to 0. And we have done this before, so we have for the expansion of sine hyperbolic alpha, alpha plus alpha cube over 6, and for the cosine hyperbolic we have 1 plus alpha squared over 2 plus alpha to 4 over 24, etc. And to first approximation, this is basically just alpha, right? So we can neglect these terms and we obtain just alpha. So we can see that the magnetization is going to be approximately n times mu b. So it was what did we find? N times mu b tangent hyperbolic alpha, n times mu b times alpha. So that is n mu b h over kt kbt. So this is of the form number c divided by temperature T. So we see that the magnetization is varying as 1 over T for a typical H value that we obtain in the lab. So the behavior of magnetization as a function of temperature is decreasing as 1 over T. Now what happens as T goes to 0? Let's see, limit as T goes to 0, that means alpha is going to infinity. We have tangent hyperbolic mu b h over kt. This is the limit as T goes to 0 or alpha goes to infinity. Sine hyperbolic divided by cosine hyperbolic, which gives us e to the alpha minus e to the minus alpha, e to the alpha plus e to the minus alpha. Now alpha approaches infinity, so these two disappear, and you can see that tangent hyperbolic is approaching 1. So what happens as T goes to 0? As T goes to 0, the magnetization approaches its saturation value, number of spins per volume times a Bohr magneton. So this is saturation. And this is equivalent to saying alpha is approaching infinity. All right. Now the other question is, what happens as T approaches infinity? Well, you can see here, as T approaches infinity, that is, as alpha approaches 0, m decreases as 1 over T. So that's what we have found in our analysis here when alpha approaches 0. So this is the behavior for high temperature. Now we want to find a numerical value of ms at t equals to 0 for a given value of number of spins per volume. At t is equal to 0, we have found that we have saturation magnetization, which is the spin density n times Bohr magnetons. So the spin density, number density, is 3.7 10 to 28. The Bohr magneton, so this is given per meter cube, so we can use SI units. A Bohr magneton is 9.27 10 to minus 24 joules per Tesla in SI units. So we find that at T is equal to 0, we have a saturation magnetization 3.4 times 10 to 5, the SI unit of magnetization is ampere per meter. Okay, so this basically answers all the questions. We know the behavior as T goes to 0, numerical value of saturation at T is equal to 0, the behavior as T goes to 0, and its dependence on temperature. Now, part E. How does the relationship between M and H reduce? What does the relationship between M and H reduce to for weak fields? H goes to 0. What is the expression for the susceptibility in this case, and how does it depend on temperature? Calculate the numerical value of chi at room temperature. So in part D, we said that typical H value is already small, so that mu BH product is much less than the thermal energy KT. So this will allow us to say the magnetization as we have found in part D is varying with temperature for small h values or large temperatures as n mu b square times h divided by kBT. So this is the MH relationship. Now what is the corresponding susceptibility? Susceptibility is magnetization divided by the magnetic field H, and it is n mu b square divided by kBt. So this is the susceptibility expression. And how does it depend on temperature? Well, we have seen that this is varying as 1 over T, because the number of spins per volume is not changing with temperature, and Bohr magneton and Boltzmann constant are both constants, so they don't depend on temperature. So the value of susceptibility in SI units at 300 K. Now we have shown in our discussion that to get the SI susceptibility using joules here instead of ergs for kBt, we end up having to multiply the CGS susceptibility by mu 0, and that comes also from the fact that we have CGS ESU and CGS EMU conversion problem here. So this is mu 0 and mu b square divided by kBt. And why? Because mu bh must be replaced with mu 0 mu bh when we use the SI calculation. Okay, so in that case, this becomes 4 pi 10 to minus 7 Henry per meter times the spin number density 3.7 10 to 28, Bohr magneton squared 9.27 10 to minus 24 squared divided by Boltzmann constant and temperature 300 Kelvin, close to room temperature. So we find that the value of susceptibility at 300 Kelvin is 0.000965. So it's a small positive value for the susceptibility. And finally, comment on the results which you have obtained for this spin system. What kind of magnetic behavior, antiferromagnetic, paramagnetic, diamagnetic, etc., is displaced by this model system? Justify your conclusion. How would we need to modify the model in order to describe ferromagnetic behavior? Okay, so the susceptibility varies as 1 over temperature, and you know that this is the Curie law for paramagnets, right? So it is a paramagnet. It has a small positive susceptibility that also shows that it is a paramagnet. And how would we modify this in order to describe ferromagnetic behavior? So we have to add an exchange interaction. So to describe a ferromagnetic behavior, we need to add exchange interaction, and that is a PHYS molecular field. And that is to say, it's the PHYS molecular field which is gamma times magnetization, so as we see in the behavior of ferromagnets. Okay, so let's go through our results of the analysis of the three-dimensional lattice of spins, each with spin 1/2. The magnetic moment of each spin is g square root jj plus 1 Bohr magneton, and j is equal to 1/2 because L is equal to 0, S is equal to 1/2. The lambda factor is 2 for a spin-only contribution, and the projection of the magnetic moment onto z-axis is found by minus g m sub j Bohr magneton, where m sub j is the magnetic total angular momentum quantum number, which varies between minus j and plus j, so it's plus or minus 1/2, and the only possible values of the z component of the magnetic moment is plus or minus a Bohr magneton. When you place a plus Bohr magneton magnetic moment in a magnetic field H that's pointing along the z direction, since they're in the same direction, you would get minus mu bh, or if you put minus mu b, you will get plus mu bh. So plus or minus mu bh energies are the possible magnetic energies for each spin. We can calculate the average moment per spin by using statistical thermodynamics. Basically, the moment multiplied by its corresponding Boltzmann factor, e to the minus ei over kt, the corresponding energy over kt. Now, when we have a magnetic moment plus mu b pointing in the z direction, the corresponding energy is minus mu bh. Minus mu bh becomes plus mu bh, so e to the mu bh over kt. And similarly for minus mu b. And we see that this average magnetic moment per spin is a Bohr magneton times tangent hyperbolic alpha, where alpha is mu bh over kt, and total magnetization, we have to multiply it with the number density of the spins. Now, for a given typical h value, this alpha is typically much less than 1, and tangent hyperbolic alpha is replaced by alpha. And if we have temperature goes to 0 or alpha goes to infinity in the other limit, tangent hyperbolic is replaced by 1. So as for typical temperatures, we have m proportional to 1 over t, and for small temperatures, t goes to 0 at very low temperatures, we reach saturation, n times a Bohr magneton, and here we have a numerical value for a given spin number density. And the behavior is decreasing as 1 over t as t goes to infinity. And this gives us a susceptibility n mu b square over kt, which is in the form of Curie law. And we can evaluate this at room temperature, and we see that it's a small positive number. But when we evaluate it using SI units, we have to be careful. Alpha is instead of mu bh over kt, we have seen here, this is CGS, it's going to be mu 0 mu bh over kt in SI. So that's why we have to multiply this by mu 0, and we obtained 0.00965, which shows us that 1 over t behavior and small and positive chi, it's a paramagnet. In order to make this a ferromagnet, we need to add exchange interaction or molecular field.